Welcome to Careless Coder. Today part 4, the final part of Ziggy Says. You hear that, Ziggy? I said it right. The final part of Ziggy Says. Motherfucker! We're finally there. I hate making these code along tutorials, but it's the easiest way to learn when I program and you follow along. So today we're going to give our lizard overlord his voice to bark his orders at us. Is that how lizards sound? Then why are we afraid of the lizard people? Why do they have dominion over us? And no, we're not going to implement that sound in PWM. I wouldn't even know where to start. We're just going to approximate the Simon sounds. And we will implement the speed up, because as the levels progress it gets harder and harder and harder, and sooner or later the dictator will get you, if you know what I mean. And then we will refactor our code, because we did this trick that we do arithmetic to derive pins, and fate had it that this tiny little Arduino RP24 board came in, and that pin layout doesn't actually match the RP2040 Pi Pico pin layout. So I needed to have a bit of an abstraction, so I refactored the code that what I also usually do in C, create a constant static array that we just pick out the numbers and we correspond the move to the numbers in that case. I will not code that completely out, I will just scan that code, because by then you should already understand enough of Zig and embedded programming to do it. So let's jump in and finalize this bitch, if you know what I mean. So last time we ended up with a working game without sound and without the increment in speed. So let's start right away incrementing the speed. This is just a simple if-then tree that takes in a step, which is of type uSize. This of course it comes from this loop. And we just do a lot of if-then else's. You could also have created something like a nice array, a static array, that will also work. But this code is nice and small and relatively fast. Okay, so we have all these steps. So every fifth step we increment the speed, with the exception of 20, because 175 milliseconds is wickedly short already. And frankly, I played this game a lot since I developed it 2 weeks ago in 4th, and then the last week here with Ziggy. And I have yet to beat the 3rd level of 15 steps. So, and yeah, my brain is 50 years old, so it's not as speedy as your younger brains, but still it shows the difficulty. Okay, let's set that in there. Let's compile this just to be sure. Okay, let's do that first. Oh, of course we need to return a 32. Then we have less debugging later on. An implicit return? Oh, else. Yeah, if there is nothing in that range, let's return 300. That's the default. You could also remove this one actually. Let's do that. Makes a bit more sense to do it then. Alright, okie dokie. So that is the speed up done. Let's do the next one. So now with the speed up done, let's do the most difficult thing. PWM. And PWM in the Pi Pico and this wrapper, I also blame this wrapper, is very convoluted and complex. That's really the only thing to say. It's really complex. Hey, I removed my constant max sequence. Oh, it's up there. It's still there. Let me do this, then I like it better. So Right, so first we will create that structure that I showed you in the first episode that we did not use for our GPIO pins because we wanted to be able to just put in the port numbers. And later we will refactor this, or I will show you my refactored code where I actually use an array. Makes it even a bit nicer. So let me first set up this global configuration thing. We are going to use GPIO 10 because that is where our piezo is attached on. Here, the piezo. You need this resistor in here. I put a 1K. Initially, I didn't do that because on Admils I hardly ever put in a resistor and it works fine. And here I had the weird issue that for some reason only button 9 every now and then just bounced when the piezo was oscillating. So I put in the 1K resistor and it was fine. It didn't reset or anything. It's just that it the switch bounced. So let's create a tuple and let's give it the name, and we give it the name piezo because that is what is attached to it. Piezo. And then we have the function. And this is a bit tricky. You have to find this in the documentation and the actual code. I had to reverse engineer the code. I am not happy with what they currently have done because I think as soon as I set GPIO 10, as a PWM, there should be a list in the hell that says, oh, that is function PWM5 if you set the function to PWM. There's no need for us to should know that. This is why you abstract things, to get rid of these stupid little details. Now, how did you find out, or how do you find out which slice and channel it is? It's using this little table that comes from the RP2040 datasheet. And I read this thing and the whole PWM chapter 4, completely because it is relatively complex compared to other PWM systems. The cool thing is every pin is a PWM, but it adds a bit of complexity, and that is this channel, that's the A and the B, and the slice. So we are currently on pin 10, and that is slice 5 channel A. And here we see that slice 5 channel A. So slice 5 channel A. Right? There we go. All right. Now let's create a variable piezo where we can put in our PWM object of type PWM. Yeah, like I said, this is convoluted. This needs to be cleaned up, in my opinion, by the developers. A, and we set it to undefined because this is Zig. We have to define everything. And the reason why we do this is so that we can actually use this globally across all our private functions. When your function is public, you should pass it always in, because otherwise you're dependent on a global variable. You don't want that. But since these are all private functions, and we do the same here with GPIO, this is perfectly fine. So let's go to main and let's set it up. So const pins equals pin config, and we just call apply. And this always needs to return a const. That is the annoying little thing. And then you need to actually assign the pin if you want to have it global, pins in this case, and then the name piezo, which is of type that we just created, PWM 5, A. Right, so now we have it. We can use it globally. Now we need to set up the pulse width modulation. And this is also where this library is a bit flaky. Like we have set level. Actually, that is more like the duty cycle. Then we go to the slice. And there we set the rep. Now this is the one that we're going to change the most. because this basically sets the frequency in combination with the set clock divide. We have the clock running. The clock is running at 125 megahertz, the same frequency as the board. And then you divide it by 4.0 later on. We will do that in the next line. But you can imagine that it's then counting up, right? And as soon as it hits this set rep, it will wrap around back to 0. So it makes sense to see, okay, we have this duty cycle, it counts up, and then it wraps over. So the larger this number is, the lower the frequency is you get on the pin output. And that is what we actually drive the piezo, right? We have here, we have the pulse coming in, and it will trigger the piezo to bend a little. And that causes the air to vibrate, and that's what sound is. So let's set up that division, because currently at 125 megahertz we don't hear a lot. So we will call the set clock divide, and we divide it by 4,0. Now there is great documentation on that data sheet here about how to calculate this. The formulas are easy, and when you read it, it's also easy to reverse engineer how it's implemented. And I had to do it twice. I had to do it for fourth, because initially I developed this in fourth, and I had no idea how to use the PWM. There it was also rather poorly abstracted. And the same here again. I was like, how do I do this? How do I set the duty cycle? And well, back then I already had this knowledge, so it was easier to figure out here than for fourth. For fourth, it took me about 4 hours to figure this out with the documentation. Okay, and then we disable the PWM, because if there's no sound, you just disable it. You would be tempted to set this to 0. It's also possible, but why keep driving the circuit if you can just disable it? Saves a bit of energy. Okie dokie, so let's create a nice function to stop the piezo. So basically we call this function. So let's call it stop beep. Stop beep. Yeah, and just call this function. Boom, done, and it returns void. We don't do anything other than that. And then let's create a function play beep. Function play beep. Right, and we put in that move, so we correspond a move 0, 1, 2, 3 to a particular sound. And we also have a move 4, which is a low pitch buzz when you lose, of course. So let's start with a switch statement. We haven't used those yet. Now I first need to set that clock back, because I could potentially, when I play step 4, lower the frequency, because there we want a lower frequency. So let's set that clock divide back to 4,0. That's the normal. Let's call it the register, the normal octave where we're in. Okay, and then we call the switch, because we haven't used the switch yet. Alright, move. So 0, this is how you set what to do. It's a bit weird in the syntax, but I do like it. Slice. And we set here that rep value. That is basically what we do. So when we play sound 0, we have a high pitch frequency, so we set it to 4,500. And to you music lovers, yes, these are not perfect keys. I know it also triggers me a little, but now I'm used to it. I didn't want to bother by calculating the perfect frequency in relation to 440 Hz A. I was like, I can't be bothered. I just want this sound to work. I want this project to be over. So you can tweak it to all your heart's content. You can use the formulas to calculate the correct pitches if you want. But the original Simon also doesn't really have a... by the way, this needs to be commas. Doesn't have perfect keys as far as I can remember, by the way. Could be wrong. And if we have 4, then this is the obnoxious loose sound. We have more than one statement, so we'll use the curly brackets. Also with the thingamajiggy, let's get this. And I lower that frequency to whole divisions. And we set the slice piezo. Let's just copy it. It's that same frequency, but just 2 divisions lower. And we have an else in case we don't match anything. Then we set the piezo slice set rep to 0. Remember what I said, if this is 0, it doesn't really count. And we always set it here and that. This one and this one. Hey, why is it? Did I miss something here? This lines up with slice. Oh, this one shouldn't be there. It was already indented even, and I did not even see that. That's the difficult thing of talking and coding at the same time. Alright, otherwise we set rep. Yeah, that's perfectly fine. Now it's good. Then we have this one. Alright, there we are, back in line. And then we set the piezo slice to enable. Because we're playing the sound, so let that slice just run. And in this case, if we put anything in that is not matching up, it's set to 0, we don't hear it anyways. Yeah, so this should work. We can now actually use this within our code base. So let's use them in our code base. The play move. Yeah, when we have a move, we just want to hear a sound as well as see the LED toggle. So let's do play beep. And let's put the move in there. And at the end, of course, we need to stop the beep. Stop beep. Let me do that actually right there. I like it before the LED. That's just a little neurosis thing. It doesn't really matter, but that's just my brain. And game over. Where there we have that obnoxious low beep that we created specifically for case 4. So let's put in case 4. And stop beep. Okay. You won. Yes, let's play a different tone for every step here. So this will alternate through the 3, and since they're not in the order of a scale, the yellow one has a bit of a lower sounding pitch. It's and the red one is higher. It gives it a nice, happy sounding thingy. That sounded scientific, right? It's a all right. Let's do a play beep here. When the key is down, we of course want to play the associated beep with the pin. So we have pin number and we need to subtract 6 because then we get the move number. We've been over that 100 times before, so I'm not going to bother explaining that again. And we will stop the beep. Alright, so let's build this. And there's an error, and there's always an error, especially with my typing ability, or lack thereof. Expected comma after initializer. You are absolutely correct, yes. Configuration.gpio, equals. Yeah, that should be there, that equals is important. And dot, and I got a dot there, and I have the comma, yeah. And I need a semicolon here as well, by the way. Oh, it's already saying that. Play beep, we need to have a void there. Yeah, like I said, there's a few things that I always forget. That is the return value in Zig. And then I'm pretty sure we also forgot it. The stop. Oh, stop beep, we got it. And capturing. And that should be a semicolon, line 60. Yep, that was a typo. Set clock division. That is. Oh, it's not. It's on the slice. It's not on the piezo itself. 52 slice because the slice is where you configure, of course, the division, because every slice can have its own division. Why is struct declared here? P8, so slice, sorry. Typo on 52, slice. And 59, the same thing, of course, because I copied it. Yep. Not slice. And it's a function. Okay, now have we cut it all? I did it somewhere again. 62. Yeah, this is why I usually don't like to type out my lessons. There we go, complete. And just go over code. But when you learn something new, it's best to just code along. And yeah, then you have to sit through my fumbling as well. So let's see and upload this where we are. Zig out. Bin. Okay, let's here. That sounds good. Another one, please. Yeah. Please a green one. Yeah, speed up is working. Yeah. That's good. Let's hear the... I want this actually lower. That's not really the sound that I'm looking for. I want it lower. So let's just reduce this clock division to 10. Make it a bit more lower and a bit more obnoxious sounding. Okay, let's see. Yeah, that is the obnoxious buzz that we want. Now let me play through to a winning situation. Yeah. Ah. We missed a stop sound somewhere. Yeah, of course, we missed it over here. Stop, beep. That's why you always need to test every situation. One more test. Now we should have it also set silent. Yeah. Cool. It's working, finally. Now when you're done coding, it's always good to give it a once over and see what you can improve and refactor. And I actually did refactor something, and something of necessity, because I got in, as fate had it, 2 very tiny RP2040s, but the pins broken out on the breakout board are different than the RP2040. They don't line up as neatly as they did here. So the arithmetic trick doesn't really work. And this is a trick that I use a lot, as you see in other embedded videos, by the way, in C as well, that I have a static array, static constant array with the pin number. So here we have the output pins 2, 3, 4, 5, input pins 6, 7, 8, 9. And you will realize that they match perfectly to move 0, 1, 2, 3. So we can just use this to translate a move into a pin. So here in the setup, we loop from 0 till 4, not until 4. We get those pin numbers, we set them to the output pins, these. And these we set to the input pins. And we also use them in the move here. I changed pin to move. So I abstracted it one level higher, basically. And that is the only major change that I did. Here as well, you have the input pins that you can press for the level. So we have 0, 1, 2, 3, and that corresponds to the actual pins. And this is actually even a bit faster because it's a constant. So the compiler will actually take these numbers out and actually put them in during the compilation process. So it's even a bit faster than the subtraction that we did, because that is dynamic and this now is becoming fixed. So that is actually a nice improvement. And that's always good, just to let your code rest for a couple of days, look over it and go like, ah, yeah, I can actually do this better. So there you have it. We finally got Ziggy Says working with sound. Yeah. I initially coded this in Forth and it took me 2 evenings in the weekend. And I implemented this in Zig in literally 2 hours. That is how easy and powerful Zig is. Yes, I also had to look into the code how to do the PWM, because the PWM abstraction also here, just like in Zepto4, is not ideal. It should be abstracted a bit more to make the programming easier. And that is something I have to hand to MicroPython. I'm actually going to say something good about MicroPython here. The abstractions are brilliant. It's so easy to program. But it's so incredibly bulky and so incredibly slow. I'm actually shaving off a couple of cycles to not do arithmetic on pins. And there you have a runtime that is as slow as diarrhea floating down the leg of a toddler. It's crap, literally and figuratively. So I hope you learned something. I hope you will create your own version of Ziggy. Get the code in the description. You don't need to type it yourself. And I'd love to see if you create one of these, how they look. Like I said, I will feature them on my videos. And yeah, I think this weekend I will try to see if I can actually use this. I love the fact that this even has a USB-C on it. And maybe get a tiny case, just put some wires on it and actually put this in a case. Because I do play Simon a lot, to be honest. Even the old one, I still turn on at least 2 or 3 times a month. So yeah, I love Simon a lot. So I hope you learned something and see you in the next one.